Okay, so welcome to the 24th class on computer architecture and organization. So in the previous class, we are discussing about these instructions, isn't it or not? So in the previous class, we have discussed about end instruction. Now in this class, we are going to discuss about the rest of the instructions. Okay, so I think in the last class, we have discussed about the end instruction and we have taken an example and I have showed how this end operation is going to be taking place. Okay, here this is nothing but intersection symbol. So why we have used this intersection symbol means whatever if both rn a particular if both rn and rm both contains 1, then only the output is going to be 1. That means it should be 1 should be common in that particular bit position for both rn and rm, then only the output is going to be 1. Okay, so that is about this AND instruction. Next, we are going to discuss about BIC. BIC stands for bit clear instruction. Bit clear instruction. See, this is one of the separate or different instruction what we are going to discuss, because in the instruction or in the instruction exclusive or these are you have this you have already got these topics in your STLD, AND gate, OR gate, exclusive OR gate. Similarly, the first 2 units also we have covered about AND and OR. See here BIC, it is a different instruction. The full form of BIC is bit clear instruction. Okay, what they are saying that bit clear instruction, this is very closely related to AND instruction. This is also one type of AND instruction, but before performing AND operation, it will perform some other operation. What is the some other operation is, see once read this line carefully. 1 second. And wait. Spotlight. Okay. See, it complements each bit. It complements each bit in the operand R1 before ending them with the bits in the register R0. See here the instruction is given like this: big R0, R0, R1. Here if you observe carefully, here these two are the same operands, isn't it or not? Okay. So big BIC, that means bit clear instruction R0, R0, R1. Okay. What is the thing that is going to happen initially means, initially see what is the last operand R1, isn't it or not? Okay, what it is going to perform is it will perform once complement on the content in R1, then only it will perform end operation with R0, and the result is going to be stored in the R0. That is the meaning of this one, big R0, R0, R1. For example, if it is R2, big R2, R0, R1, then first, see, I will explain with you with an example of the meaning of this particular instruction. Okay. See, suppose, for example, I have R1 is equal to something like what we'll take 56, 56, okay, 56H. Take this as R1. Write it in a binary form. So how can I write 5? 0, 1, 0, 1, and 6 can be written as 0, 1, 1, 0. Isn't it or not? Next. So what is the first thing we will do? The processor is going to do is, first of all, whenever it encounters this big instruction, it will identify, or it will just go through the last operand. Here the last operand is R1. So it will first see the value that is present in the R1. So what is the value that is present in the R1? What is the value we have assumed? We have assumed R1 is equal to 56H. So if you write this 56H in binary form, it will be like this. Then what the processor is going to do now is it will perform once complement. It is going to perform complement each bit. Complement each bit means it is going to perform once complement. That means it will replace 0 with 1 and 1 with 0. That means the new value will be like this. 56H is there now, so it will be replaced like this. It will be replaced with 1 0 1 0 1 0 0 1. 1 0 1 0 1 0 0 1. Okay, so its value is something like 1 0 0 1. Here 1 0 1 0 1 0 1 0 means it's 10. So 10 means A, isn't it or not? 10 means A, and 1 0 0 1 is a 9. Okay, so the total value is A9H. In hexadecimal, the total notation is A9H. Okay, its value is A9H. Okay, so in that means the 56 value that is present in R1, it just changed as A9H. It just changed as A9H. Okay, now this particular A9H is there now. It is going to perform AND operation with R0. It is going to perform a AND operation with R0. Okay, let us assume that I will write separately here. Let us assume that R0 is equal to something like how much I can take 47 H like this. So if you write it in binary form, 0100 is 4 and 0111 is for 7. So what is the value that is present in R1? The updated value in R1 is like A9H. A9H. So A means 10. It is already present here now. You just copy that one 1010 and 1001. So now these two are the values that are present. So initially I have taken R1 as some 56H. Then what is the, whenever I am going to apply this big operation, obviously it will perform one's complement to this R1. Whenever you perform an one's complement, you will get A9 as an answer. Okay. So now the value that is present in R1, the updated value, it is going to be performed AND operation with R0. Okay, so if R0 is equal to 47H and R1 is equal to A9, then I am going to perform AND operation between these two things. Okay, whenever I perform AND operation, then what is the answer I am going to get? See, you all are very familiar about AND operation. The output will be 1. The output will be 1 when both the inputs are the output will be 1 when both the inputs are 1, isn't it or not? So if you observe here one input is 0 and the other input is 1, so the output is going to become now 0, because in an AND operation when both the inputs are high, then only the output is going to be high. So here the output is 0. Similarly, the next one is 1 and the other one is 0, 0, 0, 0. Similarly here 0, 0, 0, 1. So now the obtained answer is 0, 0, 0, 0. The equivalent value of this particular 0, 0, 0, 0 is 0 and 0, 0, 0, 1 is 1. So the total answer that is going to be stored in R0 is 0, 1H. So the value that is going to be stored in R0 is equal to 0, 1H. So this is the concept of BIC. Okay, here what is the thing that is it is going to perform this instruction means whatever the last operand that is present, it is going to perform complement on that particular operand. So complement in the sense one's complement. Okay, then after performing the one's complement, it is going to perform AND operation with the another register. Okay, and the obtained value is going to be stored in that particular R0 register. So this is about the BIC instruction, isn't it or not? Are you clear? Next we are moving to the next instruction. Okay, before moving I will erase it. Okay, I got a call. Okay, so this is about the bit clear instruction. Now we are moving to the next instruction. Okay, yeah, see, now we are discussing about the topic called setting of conditional codes. See, what are meant by conditional codes? See, we are having in flags, we are having some special flags called conditional flags. That means that particular flags are going to be 1 whenever a particular condition is going to be true, is going to be satisfied. If not, that particular conditional flag is going to be 0 permanently unless a particular condition is satisfied, then only it will become 1. Rest of the cases it is going to become a 0. Okay, see, that's what they have told. Setting the conditional flag codes means what they have given. Some instructions have sole purpose of setting the condition. That means there are some instructions, their main purpose is just to set the condition. They don't do any arithmetical operations or logical operations like addition, subtraction, multiplication, shifting or moving. They don't do anything. Their main whole and sole purpose for what those particular instructions are designed is they are just used for setting the conditional flags. The best example for them is compare instruction. Okay, CMP. CMP is nothing but comparison instruction. Okay, compare instruction is very similar to subtraction. Okay, compare instruction. See, this is an important question that will be asked in the Viva also. Whenever you go for any technical interviews on any company which is based on embedded systems or something, the first question they are going to ask you is what is the difference between a subtraction and comparison. Okay, see, the main difference between a subtraction and comparison is both are both the operations we are going to perform subtraction only, but whenever you perform the subtraction, the initial values that are present, they are not same as the values that will be obtained after performing the subtraction. But in comparison, only the status of the flags are going to be changed. The initial contents that are present, they will be remain unaltered or unchanged before and after the comparison operation. See, it will be what I have told, it will be somewhat what we will call difficult for you to understand, but I will make it understand with a simple example. Okay, see, for example, here I have given an instruction called CMP RN comma SN. I will explain this instruction with comparison and subtraction. Okay, so now we are taking one text. Okay, see, for example, consider Rn is equal to how much we'll take some 35 H. Similarly, consider Rm is equal to some what we'll call some 40 H. So both are hexadecimal numbers. Now if I perform an instruction, or if I perform some instruction, or if I execute some instruction like subtract Rn comma Rm, here Rn and M, N and M indicates number. It may be subtract R2 comma R3 or R3 comma R5, like that. Okay, N is a number and M is a number. Okay, so if I write an instruction like this, subtract Rn comma Rm, then what is the thing that is going to happen here is, see, it is there is a subtraction that used to take place. That means the contents of Rn minus Rm. That means the contents of Rm are going to be subtracted from the contents of Rn, and as it is a two operand subtraction, there is no third operand, so the defaultly the result is going to be stored in the first operand. Okay, because there are only two operands, the result is going to be defaultly stored in the first operand. That means the result will store in the Rm register. So this is how it is going to happen. See, Rn minus Rm will take place, and the result is going to be stored in the Rm register. So as per our phenomena, or as per our values, if you take Rn is equal to 35H, then 35H minus Rm is 40H. So then we are going to get 35 minus 40. Actually, it should be minus 5, but as it is hexadecimal, see, 40H means if you convert it into a decimal number, 16 fours are 64. Okay, 16 fours are 64. Its equivalent value is 64, whereas it is 16 threes are 48 plus 5. 48 plus 5 is how much? 48 plus 5, 53. It is 64. 64 minus 53, it is 11. That is 0AH. If you have any doubt, you can do it by using a calculator, I think. Okay, so it is minus 0AH, isn't it or not? Because I am subtracting a smaller value from a larger value, so it is minus 0AH. Because 40 in the sense in decimal number, it is 16 fours are 64, and 35 means 16 threes are 48 plus 5, it is nothing but 53. So 53 minus 64 is nothing but minus 11. Minus 11, I am just I am not writing it in ones complement or twos complement form, because once you see in your calc, you will get an answer in a twos complement form or ones complement. I am not using any complements. I am getting minus 0AH. I just represented it with a symbolical form. Okay, so now what I am trying to say is I got a negative value, isn't it or not? I got a negative value. So whenever I got negative value, I have some conditional flags like sign flag, zero flag, carry flag, auxiliary carry, parity. The conditional flags will vary from processor to processor and version to version. Okay. So see, whenever I perform this operation, whenever I get a negative answer, I have a flag by named signed flag. Signed flag. Now the signed flag is going to be enabled. Sign flag is going to be enabled. Okay. See here, see if you observe here, after performing the answer operation, I got a 0 minus 0 AH. This minus 0 AH is defaultly, it will go and store in the register called RN. It will go and store in the register called RN. That means in RN I am going to store this minus 0 AH. This is what that is going to happen. But in the case of subtraction, but whenever I perform this comparison operation, okay, in comparison also internally the subtraction operation is going to be taken place, and it will take answer as minus 0 h, and based on that answer it will what you will call enable the sign flag, and it will check the parity also. If it is an even parity, parity flag is also going to be enabled. Like that it will do. But after this instruction, when you check the value present in Rn and Rm, okay, in subtraction the Rn of previous value of 35h is being updated with minus 0ah, isn't it or not? But whenever there is a subtraction, whenever there is a comparison, after performing of the comparison, whenever you check the values of Rn and Rm, they are not going to be changed. Okay, the Rn value is not going to be 0 minus 0ah, it will be like 35h only. That means there won't be any change in the register values after the comparison instruction. Okay, internally it will perform subtraction, but that subtraction, that results, those are intermediate results, those will be present only for that particular instruction. Once the execution of the comparison instruction is going to be completed, in the next instruction if you check, you will get the previous values as it is, previous values as it is. Are you clear? So that is the difference between comparison and subtraction. So comparison won't alter the values. The only purpose of using this comparison operation is to check the status. That means if I compare, for example, if I take this Rn also some 40h, Rn also some 40h. Now if I perform comparison, compare Rn comma Rm. So as I have told you that comparison is nothing but subtraction, isn't it or not? So whenever I perform this comparison, the 40 is going to be subtracted with 40, then I will get 0 0 as an answer. Okay, but see, my register values are not going to be updated. R0 is not going to be updated in comparison. Though you perform the subtraction, after the execution of the comparison instruction, when you check the value of Rn, it will be 40h only. It won't be 0 0. Then what is the purpose of that instruction? Means intermediately it will check this value, and as I got the value of 0, it will set the 0 flag. It will set the 0 flag. That is the only thing that it will be taken place, except that it won't change any value. So these kind of instructions are called setting condition codes. They will set or reset the conditional flags. So as they are setting the conditional flags, their purpose is only to set the condition flag whenever that particular condition is true. That means whenever I get negative result, it will set the sign flag. Whenever I get answer as 0, it will set the 0 flag. Whenever I will get a number of ones in our result as even, it will set the parity flag, like that. Okay, so these type of instructions are called setting conditional codes. The best example is comparison. Okay, that's what they have mentioned here. See, in ARM, the arithmetical and logical instructions will affect the conditional code flags only if explicitly specified to do so by a bit in the opcode field. That's what they have mentioned here. So next, setting the conditional codes. See, there are special instructions on those. By using those instructions only, we can set the conditional flags. That means, see, in the last class we have discussed about ADD instruction. ADD means it is general addition. Okay. Now we are going to discuss about a special instruction called ADDS. So what is the difference between these things? See, you can, if you read this one, you can easily understand the difference between ADD and ADDS. See, setting conditional codes is the concept. Okay, if you use ADD instruction, it does not set the conditional code flag. That means, in as per ARM point of view, whenever you use ADD instruction, it don't change or it don't alter the conditional flags. Though you may get 0 as an answer, it is not going to alter the 0 flag. Though you get a negative as an answer, it is not going to alter the sign flag like that. Okay, whenever you use the instruction called ADDS, then only the conditional code flag is going to be set. That means, if you want to change the conditional codes flags also, then there should be a suffix called yes. There should be a suffix called yes. That means, if the original instruction is ADD, if you use a suffix called ADDS, that means here we have added S, then only it will set the conditional code flag. If not, it is not going to what you will call set the conditional code flag. Okay, whenever you use the suffix yes, then only it will what you will call then only it will conditional code, it will set the conditional code flag. That is the concept. That means, if you use a general SUB, it don't change the conditional code flag. But if you use a suffix SUB yes, then only it will change the conditional code flag. Okay, so that's what they have given in this in this slide. See, this is indicated by appending the suffix s to an assembly language opcode mnemonics. This will be called as mnemonic. So in this mnemonic, we will suffix a letter called s. Whenever we will suffix this letter s, then only the conditional code flags are going to be set depending upon the obtained result. Okay, if you use normal ADD, it is not going to set the conditional code flag though the particular condition is being met. That means, if I use general ADD, the 0 flag is not going to be enabled though the answer is 0. The sign flag is not going to be enabled though the answer is negative. Are you clear? That is the concept that was present here. Okay. Next, input operations. This is the another concept. See, what we are trying to say is the ARM architecture uses memory mapped IO operations. See, IO means input output operations. Memory mapped IO operations means if you take some data from an input device, if you take some information from an input device and you will place it into a memory. Next, whenever you required, you will take that particular required data from memory and you will place into the output device. This phenomena will be referred as IO operations. So the ARM architecture uses memory mapped IO operations. What we will use? Memory mapped IO operations. So what are these means? See, whenever there is an input device, what are the best examples for our input devices? Keyboard, mouse, joystick, isn't it or not? So you may, whenever you enter a data or whenever you type something on your keyboard, okay, it should be read by our processor, isn't it or not? So reading a character from a keyboard or sending a character to the display can be done using a programmable controlled IO. This is what we have discussed in our second unit or first unit, programmed controlled IO. That means if I am typing something on my keyboard that is going to be displayed on a processor, it will be that is going to be displayed on a monitor. This phenomena will be taken place by a processor controlled IO. What is the processor? If you use i3 processor or i5 or 7, that is the processor, and it will depend upon the software what you have used, MS Word, Excel, like Windows XP, Windows 8, like that. Okay, so what is the thing that we are trying to teach you is, see, there will be an IO program controlled IO. That means a program is there which will control the input output operations. What are the input operations? Reading something from a keyboard. That means if someone like me text something or enter something, that should be read. Okay, and if I use this mouse and if I click on something like this and the meeting, it should be ended. Or if I click on a new slide share, there should be some operation, that equivalent operation that should be taken place. This all will be taking place by this. This all will be controlled or looked after by this programmed controlled IO. Okay. Here we have given some examples. We are having some control flags. Flag is a single bit binary data storage device, just like a flip flop. Okay, here whenever a particular condition becomes true, then only the flag will become 1. In rest of the classes, the flag will be 0. So we are having here two control flags, S in and S out. S in and S out, serial in and serial out. Where, okay, next keyboard data in and display data out are located the address. This is something they have given that is not required. Yeah, here we have written or we have developed one a read and write loop. What is mean by looping? Looping means repeatedly, continuously executing some fixed sequence of instructions. That means if I have some 4 instructions, if I want to execute them some 10 times or 20 times, then I will place them in a loop. Isn't it or not? In C program, you are having while loop, do while loop, for loop, if loop. All these things are there, na? So here a read and write loop. Here we have just giving some example. The main thing what I want to say is what is the purpose of this instruction LDR and what is the purpose of this TSD. That's what I want to say. Okay. Here what is the first instruction I have? See, read wait is there now. Here this will be referred as a labels. In the next classes we will come across a concept called label. Label is nothing but it indicates an address. Okay, as it is very difficult for me to indicate to memorize the address, I will just replace that address with a name. I can place my name also. Instead of read wait, if I write MOHAN, it is not error. You can write your name also without any what you will call spaces, and you should start with what you will call with a letter. All these things are there, so you can place your name also. So it will be referred as label. Okay, here this is the first instruction. LDR. LDR means LDR R3 comma content of R1. So what is the purpose of this LDR? Here LDR reads a character. It is going to read a character. So from into which it is going to read? It will read a character into, one second. So it will read a character into R3 register. So whatever that is present in an R1, okay, that means it is going to be read into an R3 by using an instruction called LDR. Okay, so what is R1 means? Whenever I press A, that is its equivalent ASCII value is going to be stored in the R1 register. Whenever I press some C, its equivalent ASCII value is going to be stored in the R1. Okay, it is going to be moved into R3 register. Next instruction is TST R3 comma #8. So what does it mean? Testing. Testing is nothing but it is similar to an AND operation, bitwise AND operation. Bitwise AND operation means 8 is there now. I will write 8 in a binary form as 1000. 1000. So I will test the value that is present in R3 with this 8. That means I am going to perform bitwise AND operation. Okay. Next, based on the result, if both are equal, BEQ equal, if the bits are equal, then once again I will go to the read write. Read write, this is what I have told you previously. The read write is nothing but a name of the label. Okay, whenever this condition is satisfied, what is the condition? If they are equal. Okay, if both are equal, what the both whom we have tested? That means if the value of R3 is equal to 8, okay, below or equal, okay, then I am going to this read write loop. Again I will go to this read write loop. See, this instruction branches back to the read if the result is 0. So BEQ means if it will branch to the read write if the result is 0. That means it will just check. Okay, what it is going to check? It will check the R3 value. Here TST it will perform. See, I will explain you with an example. If not, it is not going to be that much understandable. See, for example, consider R3 is equal to something like this 12. or if it is possible 45H. Okay, similarly the other value is 8, so it is better to take single value. R3 is equal to 5H. It can be written as 0101. Similarly, the other value what they have mentioned here is how much? What is the other value they have mentioned here? Here they have mentioned 8, isn't it? 8 is itself, it is hexadecimal or binary or decimal, both are having same value. So 8. How can we write 8? 1000. 1000. So test is nothing but end operation. So whenever I perform test operation, what is the result I am going to get here? See, it is going to perform bitwise end operation. So whenever the end operation between 0 and 1 is 0, similarly 1 and 0 is 0, 0, 0. So the answer what we are going to get is 0. So what is the meaning of this one? BEQ. BEQ instruction, what it will do means it will say check the result. Here the result is equal to how much? 0. So whenever the obtained result is equal to 0, it will again move to this particular address, particular label. Here the name of the label is read write. That particular label is present here. That means my controller will come here again and it will execute this particular instruction. Okay, my controller will again comes to here and it will again execute this instruction. Next again it will check the value. Okay, if it is again equal to 0, then automatically it will come here. So that means here there is a loop operation. The same instructions are going to be executed multiple number of times. Okay, so this will be called as looping. Okay, see, the instruction branches back to the read write if the result is 0. Now assume that the output status is loaded with a register R2. So that is the read operation and here it is a write operation. For example, LDR R4, R2 I have written. That means the value that is present in the R2 will be loaded into R4. Here also I have done, I have tested R4 with 8. Here also what are the same thing? BEQ write wait, that means if it is read wait, it should be read wait. Okay. The above instruction sends characters into the R3 to data out register. When displayed is receiver ready to receive. It is not write read. It is if it is write read, it should be also write read. Okay, there is an error. Okay, so it will just go to this particular loop. These kind of instructions we'll learn in detail in the next classes. So at present, just remember that this is nothing but a label. So why we will use these labels means instead of giving an address, it is very easy for us to remember it with a label. So whenever I mention this label in my program, this is a condition. Whenever this condition is true, automatically my controller will not go to the next instruction. It will just go to the address where this label was written. Here it is not write wait, it is write read. So here it is good. Here it is read wait now. So this is the name of the label. So here the condition is BEQ. So it will test R3 with 8. Testing is nothing but performing of an end operation. So when the answer is 0, then obviously the controller will go to this read wait label. This read wait label is present in the first instruction. So it will again come to the first instruction and will execute from these instructions. Okay, that is this concept. I think all of you clear now. So next class we are going to discuss about the remaining small topics. I think everything completed. Okay. So if any, I will teach you in the next class, or this is the completion of third unit. Okay, from Thursday we are going to discuss about the fourth unit. Okay, and you are going to have a exam, one more exam on the next week on this third unit. Okay, I will give material by the end of this week. Okay, thank you.